То ми, мабуть, ну, ми не заперечуємо. Добре, ми
Ілля, Лукин, and
звук
present second part.
вимикаємо.
Please, Ілля, you're welcome.
The second part concerns with two-dimensional systems, and we will consider two-dimensional system on the infinite lattice with some form of translational invariance, as this kind of system is easier to deal with. On our previous meeting, we have discussed the entanglement entropy and the area law, which states that the entanglement entropy of the ground state of some local Hamiltonian on the lattice, and if this entanglement entropy is computed for some region A, then the entanglement is proportional to the area of the boundary of the region A. So this entanglement entropy is bounded by the perimeter of this area, and so it is usually quite small. And physically we can explain this by the fact that spins or some boson modes or some fermion modes are usually entangled only with their neighbors. So the entanglement is in some sense short range, and this short range distance of the entanglement leads us to the area law. So we have now a natural question: how we can efficiently represent the two-dimensional system wave function in some tensor form that will naturally obey the area law by construction. And the answer to this question is the so-called PEPS wave function. PEPS means projected entanglement pair state wave function. And graphically in the tensor network notation, it can be represented as follows. So if we have some two-dimensional lattice, then we place a tensor, identical tensors, on every node of this lattice. And these tensors, they have one physical index that corresponds to the Gilbert space on this node, and four auxiliary indices which corresponds to entanglement degrees of freedom. And it can be proved that for such state, the entanglement entropy is bounded from above by the perimeter or the area of the boundary of the region A. So this kind of wave function naturally obeys the area law. And the converse is also true. So if we have some two-dimensional gapped system with ground state obeying the area law, then we can approximate this ground state by the PEPS wave function to some accuracy, and the accuracy of approximation depends on the band dimension D, as we have already discussed for one-dimensional system. This band dimension D is the dimension of these auxiliary indices of the tensors, which are contracted in the definition of the PEPS wave function. We have to note that for gapless systems, for example, for systems with broken continuous symmetry, where we have gapless Goldstone bosons, for this kind of system, we can also approximate the ground state wave function to the high accuracy with the PEPS wave function. So for nearly all two-dimensional systems of interest, we can, in some sense, use the PEPS wave function ansatz as our guess for the exact ground state wave function, and we can use it to describe various two-dimensional phases of matter. For example, we can describe topological phases, chiral spin liquids, general gapped spin liquids, gapless spin liquids, valence band solids, or some symmetry broken phases like magnetics. Let us now discuss how we can deal with the wave function in the form of PEPS.
Ilya, I have one question regarding the two-dimensional system about symmetry broken phases. What about Mermin-Wagner theorem? So how this approach deals with this?
So we are discussing the two-dimensional system at 0 temperature. So we are only interested in the ground states. And for two-dimensional systems, the Mermin-Wagner theorem works only at finite temperatures. So if we have discussed some finite temperature system where we can approximate the density matrix with also some kind of PEPS, then we would naturally obtain not symmetry broken phase. But for 0 temperature, we can obtain on also symmetry broken states. For one-dimensional system, so the situation is even more difficult, because one-dimensional system cannot have continuous broken symmetry even at 0 temperature.
Okay, yeah, everything is right. So in principle, it can work also as an extension to non-zero temperature.
Yes, we can work at non-zero temperature, and there are a lot of algorithms that were developed in recent years to deal with finite temperature, but these algorithms are different from our methodology which we use for 0 temperature.
Okay, thank you.
So,
hold on a minute. I have a question, Ilya. Can you return to the previous slide? Okay, so can we quickly recall what was the previous time about the picture? I mean, the previous week. So we have a subsystem, the system of 2 subsystems, yeah, that's limited by the region A. Yeah, for example, the first one is a system.
yes.
It is interesting. All right. And my question is, so as far as I understand, that the area law tells something about the entropy of the entanglement, and the entanglement goes for the between what? Entanglement of what might be? The particles.
This is entanglement between the spins in the region A and the spins in the region B.
So if you consider the lattice, that means you're, well, considering the entanglement, for example, with the sides on the between the spins on 2 different adjacent sides, what?
We consider the total entanglement between all spins in the area A and all spins in the area B.
Okay, so it works like this. You sum up somehow, include all the spins from the area A, include all the spins in the area B, and then somehow figure out the entanglement this way, yeah? Or,
yes, there are some numerical definitions how you can define such entanglement.
all right, okay, thank you.
Any questions left? Okay, so I will continue. So the next question is how we can compute any observables of interest with our PEPS wave function. So the first question, how we can compute the normalization of this PEPS state. So we have to contract the PEPS ket vector and its complex conjugate. And this contraction, it is shown on the slide, and it results in some sense in a two-layer tensor network with all its indices, both virtual and physical, contracted. So in fact, we have to calculate this kind of tensor network to obtain the norm of the PEPS wave function. And if we want to compute the average of some observable on this lattice, then we should also contract such two-layer tensor network, but with matrix of the observable operator included between these two layers, like is shown on the slide. So the general problem of computing of observables with PEPS or IPEPS wave function is to contract some kind of two-layer tensor network with summation over all indices on the both layers. And this problem is usually exponentially hard. It can be solved exactly only for some integrable systems of statistical mechanics. I will perhaps describe in some details this later. So in the general case, this exact contraction of such two-layer tensor network, it is exponentially hard to do both, to do numerically, and it is impossible to contract it analytically. So we should develop some approximate approaches to the contraction of such two-layer tensor network. And here we show how this contraction can be done in some detail. So we can group two tensors from the two layers into one. And as a result, we have obtained one layer tensor network with some double tensors. And on our previous meeting, we have discussed that the partition functions of the problems from classical statistical mechanics can be cast in the form of the contraction of such one layer tensor network. So finally, we have found that to compute observables with PEPS wave function, we in fact have to approximately solve two-dimensional classical statistical mechanics problem on the lattice. Like, for example, two-dimensional easing model. And there are some PEPS wave function which norm can be exactly cast in the form of the partition function, for example, of the classical easing model. And our problem can be formulated now as follows. We should find a numerical method to calculate the partition function of the classical statistical mechanics problem on the lattice, which is defined with arbitrary tensor M on every node of the single layer tensor network. Any questions at this moment? So we cannot exactly calculate the IPEPS wave function norm or operator averages, and we need some approximate methods of tensor network contraction. And there were proposed a lot of different approaches how we can approximately contract this tensor network. For example, using corner transfer matrix, which was originally developed by Rodney Baxter, or so-called tensor renormalization group, which is a kind of renormalization group transformation applied to tensors. And we can also use some kind of boundary metric product states approach, which was originally used to solve some integrable classical systems. And of course, we can also use some Monte Carlo sampling to calculate observables, but usually this is more demanding approach than, for example, corner transfer matrix renormalization group. And our work concerns with the development of the approximate methods of tensor network contraction on the honeycomb lattice. And we have proposed a new version of the corner transfer matrix renormalization group on the honeycomb lattice. We will discuss it in more details in the following, but now we will discuss more common form of corner transfer matrix renormalization group, which is applied to the square lattice. And later we use these corner transfer matrix renormalization groups to calculate energies of PEPS wave function and also to obtain the wave function itself using variational optimization of the energy functional for these PEPS wave functions. And we have already applied it to the Heisenberg model on the honeycomb lattice, and also more recently we have studied the Kitaev model on the honeycomb lattice also. So the general idea of this corner transfer matrix is to divide our tensor networks on the square lattice into 9 different parts. These parts are 4 corners, 4 rows, and 1 additional tensor between these rows and corners. And then we make a following approximation. We approximate all these tensors in one corner of the lattice with just one matrix C. And we call this matrix the corner matrix. And we make an approximation that the dimension of this corner matrix is some finite value, which we called Xi. And usually we hope that this dimension Xi can be chosen as a quite small value, bounded above by several hundreds. And so the idea of this corner transfer matrix is to approximate this infinite number of tensors, or very large number of tensors, by a small matrix C and some tensors, row tensors T, which describe all these nodes or sides of the lattice on the line. And of course, we cannot do this approximation exactly, but we can carry the calculation for different values of C and then compare the results and find if the results converges to some finite value. And now we have a following problem: how we can find these corner matrices and row tensors which will efficiently approximate all this infinite number of sides in the one of the corners of the lattice.
So concerning the idea, maybe could you? So it's just a matter of division. So you divide in this particular way to then to exploit some symmetry of the lattice, right? So that all four corners are similar and rows are similar. Or there is more behind this idea?
There are more, because in principle these corners can be nodes similar to each other, and they can be not symmetric, but the division in such a form is it was developed because we can solve some integrable systems with such kind of division. For example, Baxter has solved some, no, for example, hard hexagon model was solved with such corner transfer matrix approach, and was solved exactly. And later it was found that such division can be applied to any model without it being integrable. And so it has grown to a numerical approach which can be used to study every lattice system or any square lattice tensor network.
Okay, so it's kind of a evolutionary development from integrable models to non-integrable models.
Yeah.
So
Yes, in fact, a lot of tensor network methods were some kind of numerical development of the analytical problems which were solved in the context of integrable systems.
Okay, thank you.
So the next problem is to how we can find these corner matrices and row tensors. And there is some kind of growing procedure that allows us to find this corner matrix iteratively. So we have proposed that this matrix, this corner matrix C, describe an infinite number of sides of the original lattice. And if we add additional row or additional column to this infinite lattice system, then it remains in fact infinite. So this matrices C should obey some form of self-consistent equation, which describes that the growing of the lattice does not change the corner matrix. And this is shown on the slide. We can grow the lattice with some new lattice tensors A and some new row or column tensors T. And then we can reabsorb this new row tensors T and new lattice tensors A back into the corner matrix, or we can reabsorb it back into the row tensor. And as a result of this reabsorption, we obtain some new corner matrix C and some new row tensor T. And if we have obtained the final converged C matrices and row tensors, then this kind of growing step should not change the corner matrix. So our numerical approach is as follows. We initialize in some ways the initial corner matrix and the initial row tensor T, and then we start growing the lattice and reabsorbing these new tensors A back into the corner matrices. And we iterate this procedure until the convergence of the corner matrix and row tensor. And usually for convergence, we need only about 20 iterations of such growing step. But for critical systems, the number of iterations can grow up to several hundreds. So it is usually more difficult and time-consuming to use this approach for critical systems, but this is always the case because even, for example, Monte Carlo sampling is usually much harder for critical systems, and this is also the case for the tensor network methods like corner transfer matrix or boundary metric product states approach.
What criteria do you use to find out whether it is converged or not? What do you compare between iterations in particular?
Okay, there are several metrics how to find convergence, but I usually use eigenvalues of the corner matrix. Because in fact, there is some form of gauge redundancy in the definition of corner matrix and row tensors. And this gauge redundancy, in fact, can change the corner matrix in the iteration step, but it will not change in any physical observables in our calculation.
So you mean kind of unitary transformation, kind of rotation, right? So
yes.
They are determined so up to this unitary rotation then.
Yes, and in fact, this unitary rotation can be used to take the corner matrix into the diagonal form.
Okay, thanks. Yeah, it's clear now.
I have kind of question about the how you choose the initial forms of C and T matrices and tensors. Are they absolutely random or what? And if so, why are you so sure if they're random? Why are you so sure that they will? Sorry, I forgot about the what after some finite amount of steps give you the non-different result. Converge, yeah.
So okay, in fact, we can use the random initial values and it will converge to the same result. But if we want to make convergence faster, then we can find some more physical methods to initialize the corner matrix and row tensors. And I use some form of physical initialization because it allows me to decrease the number of iterations needed for convergence.
Yeah, that makes sense. Which one? That's what I'm interested in. So how do you physically find like the closer look of the matrix C and matrices of C and T?
I usually initialize it with the initial tensor A with two indices, for example, the index above and on the left contracted between each other. So this initialization has some information about the tensor A.
All right, okay. Still have to think about it, but yeah, all right, thank you for the answer.
There are several methods of initialization which are used in the literature. It depends on the author.
Yeah, oh, okay, okay.
And so in our work, we have studied the honeycomb lattice, and we have developed corner transform matrix renormalization group on the honeycomb lattice. Our approach is as follows. In the first step, we divide the initial honeycomb lattice into the 6 corners. And then we approximate every corner as a corner matrix C. Then we also define 2 types of rows or columns. And these rows and columns are also approximated as some form of row or column tensor T, but for the honeycomb lattice, we should introduce two different tensors, left and right. We will use the notation L and R in the following. And the next step is also to grow the lattice. So we can add additional rows to the initial corner. And this will result to larger corner, but we should always remember that in fact the corner is infinite, so this growing procedure does not change it. And so we reabsorb these row tensors L and R and some side tensors back into the corner matrix, and then we can diagonalize it and reabsorb the matrices W from diagonalization back into the row tensors L and R. In fact, this is this gauge redundancy which we have already discussed. And using such a growing procedure, we also can iterate it and until the convergence of the corner matrix C and of the row and column tensors L and R. And now we can, for example, use this new corner matrices C and row tensors L or R to compute some form of operator averages for our PEPS wave function on the honeycomb lattice. For example, we show here the calculation of one side operator average and the calculation of some form of two-side operator average. And we should note here that the method shown on the slide, in fact, depends on some additional symmetries in the form of rotational invariance of the lattice and also of the chiral symmetry of the system. In fact, we can develop it further and we can apply it with some additional developments also to not rotationally invariant wave functions and to not chiral symmetry invariant and even to not translational symmetry invariant systems, but at the moment we have left it to the future work. And we show here only the simplest honeycomb lattice corner transfer matrix renormalization group, which works for translationally and rotationally invariant systems. And so now we can compute any observables on the honeycomb lattice. And the natural question is where we can apply this method. Can we, for example, take some kind of system on the honeycomb lattice, for example, Heisenberg model on the honeycomb lattice, and then optimize some IPEPS wave function on this lattice to approximate the ground state wave function. And to find this ground state wave function, we should not only obtain the way how to calculate observables, but also to develop the way how to optimize the PEPS wave function. And for this optimization, we use the so-called automatic differentiation. This kind of mathematical methods was originally developed in the field of the machine learning. And its general idea is as follows. We code our program using only so-called differentiable procedures. So these are some functions which can be differentiated through. For example, all matrix multiplications, all kinds of matrix vector multiplications, singular value decomposition, eigenvalue decompositions, all these mathematical methods can be differentiated. And we should use in our program only such procedures. Then we use these procedures to, for example, calculate the energy of the wave function or some kind of other function of interest which we want to optimize. And then we can use various automatic differentiation packages, for example, TensorFlow or PyTorch, which automatically produce the gradient of our computation of the function of interest. So our optimization of the PEPS wave function concerns from this procedure can be carried as follows. We program the energy computation of the IPEPS for some fixed lattice model with only differentiable procedures. And then we use these automatic differentiation packages to automatically compute gradients of this energy. And then we can use these energy gradients to optimize the IPEPS wave function and to find the PEPS wave function which approximates the ground state of the chosen Hamiltonian. And as we have already discussed, on the honeycomb lattice, we can use this honeycomb corner transform matrix to compute the energy of the PEPS wave function. And this honeycomb corner transform matrix renormalization group consists only from the differentiable procedures for like tensor multiplication or some form of eigenvalue decomposition. And then we can just differentiate through this energy computation, and as a result we obtain the gradients which we use to optimize the IPEPS ansatz. So our approach was as follows. In the initial step, we have chosen some kind of parameterization of the wave function, and this parameterization was an IPEPS wave function with some fixed band dimension and some fixed symmetries. For example, we have chosen our PEPS tensors as rotationally invariant tensors. And then we have approximately computed the energy of this chosen PEPS wave function using honeycomb coordinate transform matrix. We have found the energy gradients with the help of automatic differentiation package Zygota for Julia programming language. And then we have used these gradients to optimize the PEPS wave function using some form of conjugate gradients algorithm. And let us now consider some models of interest which we have used to test the approach. The first model was the antiferromagnetic Heisenberg model on the honeycomb lattice, which is defined by the following Hamiltonian with a sum over all bands of the lattice. And in fact, we know that the ground state of this Heisenberg model is antiferromagnet, but with quite large entanglement and with some quite difficult correlations. For example, the magnetization of this model ground state is about a half of the magnetization of the nil state. So this ground state wave function cannot be approximated by the nil state. It has reduced magnetization and high entanglement. And to approximate this ground state, we use PEPS wave function ansatz with different band dimensions, starting with 2, and the largest band dimension we have used in our calculation was 7. We have used the honeycomb coordinate transform matrix and Zygota auto-differentiation package to compute the gradients for this PEPS ansatz for the ground state wave function, and then conducted optimization with BFGS algorithm. And next we show some results for this model. So the most accurate result for the ground state energy obtained by the variational Monte Carlo approach was, it is shown on the slide, and we have also shown the results which we have obtained with our IPEPS ansatz. And we can see that the difference between these most accurate Monte Carlo calculations today and our IPEPS calculations is only in the 5th number. So it is smaller than 10 in the power minus 5. And our results are perhaps one of the most accurate today for this kind of models. So this IPEPS approach is very accurate for highly correlated systems, both for 2-dimensional, 1-dimensional, 3-dimensional. We have also shown on this slide how the energy converges with band dimension D. We can see that, in fact, the error in the energy usually decreases exponentially with the band dimension. So for band dimension D about 7, we have very accurate results. The results for magnetization are somewhat worse, because usually some long-range correlations of the wave function can influence the magnetization, and it is a known problem that it is very difficult to obtain the right value of magnetization using tensor network approaches, but we have used some forms of interpolations to obtain quite accurate results also for the magnetization. And this...
Yeah, I have a question regarding magnetization. So you said that in the honeycomb lattice, you do not have this ideal nail type state with large magnetization. And now you see in your tensor network approach that the approaches from the high values to low values. Can we say that this is particular manifestation that we underestimated entanglement at small d, and then we account for all entanglement between the spins in the honeycomb lattice, so to say?
Yes, in fact, if we have chosen the band dimension d equal to 1, then we would obtain the mean field solution in the form of the nil state. And then we increase the band dimension d, and increasing it, we add some entanglement and some correlations to our mean field ansatz. And
so,
the
non-local correlations, yeah. So
yes, we add local correlations, but in fact, for large values of d, for example, for d equal to 6 or 7, we have correlation lengths equal to up to 100 of sites. So this is no longer some sort of local correlation. It can be quite long range for large d.
okay, thank you.
And there are some forms of here you can see the value of correlation lengths, and it can be quite large. And we, in fact, can use these correlation lengths to interpolate our results to the infinite value of band dimension d. For example, on this graph, on this plot, we can see that energies depend linearly on the correlation, on the approximate correlation lengths of the IPEP's ansatz, and we can use this linear dependence to extrapolate our results to the infinite value of the band dimension. So we can conduct our calculations only for some small finite value of band dimension, for example, 6 or 7, and up to 10 perhaps. And then we can use these scalings to extrapolate our results to the infinite band dimension. And this is similar to how, in the context of Monte Carlo calculations, we use finite lattice scaling to extrapolate our Monte Carlo results to the limit of the infinite lattice. So this is a sort of finite size scaling analysis, which we can use to extrapolate our results. And the second model that we have studied is the ИТФ model. We have not finished our investigation of this model. We have obtained only preliminary results, but we suggested it to add some of them into this presentation. So the ИТФ honeycomb lattice is not exactly rotationally invariant. This is the model where we have three types of bands, so-called X bands, Y bands, and Z bands. And on these bands, we have different kinds of interactions. For example, the interaction of the bound of the type X consists only from the X projection of the spins on the sides of the lattice. And this model is quite well known because, in fact, it can be solved exactly using two-dimensional fermionization duality. We can compute the fast diagram of the model, and we can exactly find the ground state energy and its nature. In fact, the fast diagram of this model is quite interesting because it contains both gapped spin liquids and chiral spin liquids, and also gapless spin liquids. So there are a lot of different topological states of matter that can be observed in this model. And we were interested in the ИТФ model because we want to know if our ansatz applies to some topological states or gapless spin liquids. We should note that also the model is not invariant under rotations of the lattice. The model is in fact invariant under some form of the modified rotation. This modified rotation consists of the simple rotation of the lattice, followed by the unitary transformation of the spins. So this is a kind of modified projective representation of the rotation group. And in fact, we can use this modified rotational symmetry to represent the IPEPS wave function with some approximately rotationally invariant tensors, and then to use our honeycomb corner transform matrix to optimize the wave function. And here we show our ansatz for the IPEPS tensors. These are tensors with 4 indices, 1 physical index C and 3 auxiliary indices. And we chose this tensor of the IPEPS to be not exactly rotational invariant, but as a tensor which is rotationally invariant up to some unitary transform of the physical index. And we have found that even for such tensors, we can apply the honeycomb coordinate transfer matrix methods, which we have previously developed, and then to use it to optimize the wave function. And so we have applied our algorithm to the Kitaev model, and we have found the energy of the ground state quite close to the exact energy obtained in the exact solution of the Kitaev model by Kitaev himself. But we cannot show the results for magnetization and also some additional structures that originate from the topological nature of the ground state wave function, because this is a work in progress at the moment. But these results show that in fact we can use the methodology to study gapless spin liquids to quite high accuracy using these variational IPEPS ansatz. And so let us now discuss some future research directions. First of all, we would like to modify our honeycomb lattice coordinate transfer matrix to apply it to systems with larger unit cell, to Kagome lattice, and also perhaps to chiral spin liquids, because chiral spin liquids at the moment are quite interesting phase of matter, which is very difficult to study with common numerical methods. It is usually at the moment studied with Demer-G algorithm on the cylinders with some finite length in one of the direction, but this approach is only approximate, and usually these Demer-G calculations do not represent some interesting topological properties of the chiral spin liquids. We also can apply our method to frustrated antiferromagnets, for example, with long-range interactions, because our approach is not bounded to some models with only nearest neighbor interaction. In fact, we can very naturally extend it to models with interaction between quite long interaction. In the moment, we are also studying quite exotic subject on the application of the IPEPS to the problems on the hyperbolic lattices, because these models were recently realized in the context of circuit quantum electrodynamics. And so it is interesting if we can apply tensor networks calculations on these hyperbolic lattices, especially to the frustrated systems. We have also can try to extend this honeycomb lattice coordinate transfer matrix to triangular lattice coordinate transfer matrix, which will be interesting because there are a lot of quite strongly correlated and entangled state of on the triangular lattice, because triangular lattice is naturally geometrically frustrated, and so there are a lot of spin liquids or valence band solids which can be found on this lattice. And also it is interesting if we can further develop this class of approaches to apply it on the three-dimensional systems, because at this point there are only a few papers on the application of tensor networks to three-dimensional systems. It is generally quite hard to study three-dimensional systems with tensor networks, but it is not impossible, and we should develop some new numerical approaches with low computational cost, which will allow us to study also three-dimensional systems. So thank you for your attention. Please. Any questions?
Yeah. So maybe regarding the last point, I would like to comment a bit. So for me, this IPEPS for 3D cases looks quite an interesting perspective, because this matrix or normalization group then doesn't suffer from such increase of cost with the dimensionality, right? So it's more or less comparable to two-dimensional case, not such extreme as in kind of methods, standard methods. Am I right?
In fact, there are some problems with scaling of the dimension, but it seems that they can be alleviated by some clever tricks. And
okay. Other questions? Питання?
Можно вопрос?
Да.
Илья, а вот так вот на пальцах, чем вот преимущество этих 6 по сравнению с 4? Ханикамп против вот этого вот кубик, квадратик.
Проблема кубика в том, что вот таких вот углов на кубической решетке будет гораздо сложнее определить. Вернее, это можно сделать, но их будет больше, ну, как минимум 8. И вам придется вычислять сумму по вот такой вот как бы фигуре с 8 углами, и окажется на самом деле, что такое вычисление, оно имеет очень высокую скорость роста с bound dimension d. То есть сложность вычислений будет расти где-то как d в 14 или даже в 16 степени. Это очень быстро сделает вычисления с большими d, ну, там, не знаю, даже 6-7 почти невозможными на большинстве компьютеров.
Ясно, спасибо.
А как быть, Илья, с переходом, там, помните, в прошлый раз вы нам показывали, как перейти к непрерывным, к непрерывному случаю. Здесь, видно, проблемы будут те еще. Ну, от дискретного к непрерывному.
Ну, вообще говоря...
Общий вопрос, да?
Да,
это двумерные системы.
Ну, пусть, да, двумерные.
Вообще говоря, есть работы, которые попробовали перейти к непрерывному пределу и для двухмерных систем, но эти работы на данный момент, скажем так, чисто аналитические. То есть никто еще не пробовал использовать какие-то численные алгоритмы. Но это любопытная тема. Скорее всего, она получит продолжение. Ну и, как мне кажется, в принципе, потенциально возможно проводить вычисления и для двухмерных непрерывных систем. Но понадобится дополнительная работа.
Ну, куда ж. Добре, дякую.
У меня еще будет вопрос. Я, возможно, просто не заценил суть, но метод, по-моему, элегантный, но вот не пойму основную вещь. Для тензорных сетей, вообще глобально метода, в чем его сильное преимущество? Потому что методов есть много, он быстрее считает, он точнее считает, и вот как бы сколько это вообще занимает, условно говоря, твоего
Ну,
времени?
самый главный плюс у тенсорных систем нету проблемы знака. То есть какая проблема основная у Монте-Карло вычислений? Это то, что всегда есть проблема знака, и когда вы начинаете работать с фермионами теми же, или, например, с фрустрированными системами, то у вас начинает крайне быстро возрастать скорость для того, чтобы результаты какие-то сошлись. Для тенсорных систем проблемы знака не существует в принципе.
Что за проблема, Илья? Потому что тут как с маленькими детьми надо осторожно обращаться, потому что они следующий вопрос зададут. Поэтому есть такой неспортивный подход. А почему надо говорить? А потому что перпендикуляр. Дальше они не могут просто слово перпендикуляр спросить, поэтому заканчивается.
Ну, проблема фермионного
в
знака в
чем-
русскоязычной
в чем
литературе.
знак? Да, в чем проблема? Можно
Но
быстро.
проблема в том, что методы Монте-Карло, они же основываются на том, что вы можете какую-то положительную величину сэмплировать. То есть
Это я
какими-то...
еще могу задать такой вопрос. Слово не
Да.
перпендикуляр.
Для фермионов обычно получается, что вы должны сэмплировать величину, которая меняет знак, и это обычно крайне сложно.
Ну,
Так,
ладно.
я что-то не пойму, что в фермионах меняет знак? Потому что, как бы, ну, в смысле...
Ну, при вычислении
Да,
средних.
при вычислении средних у вас там будут величины менять знак, когда вы считаете с фермионным действием в алгоритмах Монте-Карло. Это иногда такого не возникает, например, если вы работаете с моделью Хаббарда с половиной заполненностью, но обычно немного отойти, и уже все плохо.
Ну, более волновой функции, да, при перестановке двух частиц в многочастичной волновой функции у вас получаются соответствующие средние, меняют знак, и когда вы просто с помощью случайных алгоритмов пытаетесь произвести вычисления, у вас всегда возникают вот такие проблемы, что вы расположенные знаки у измеряемых средних, и они компенсируют друг друга, и вот шум случайный вот этот, он практически гасит все полезные сигналы при вычислении средних.
Окей, хорошо. В смысле, это буквально из-за антисимметрии функции фермионной возникает. Окей, я понял.
Но это иногда еще и для спиновых систем, кстати, возникает, когда они сильно фрустрированы.
Да. Аналогичная проблема как и у фермионных систем, так и у фрустрированных спиновых систем. Совершенно верно.
Что вы имеете под словом фрустрированный? Понимаете, точнее?
Когда обычно непонятно, каким будет волновая функция, потому что в Гамильтониане есть несколько типов взаимодействий, которые каждая пытается какой-то свой тип состояния основного выбрать. И то есть они как бы компит между собой.
Я понял.
Соревнуются между собой в том, какой будет волновая функция.
Okay.
Ну и то есть, в принципе, во-первых, у тенсорных систем вообще нету этой проблемы. А с другой стороны, вот как здесь видно, что точность, в принципе, почти такая же, как у Монте-Карло можно получить.
Да, но вопрос, если можно получить точно такую же точность, она работает, как бы она быстрее работает. Если она там раза в 4-5 медленнее работает, это небольшой профит. Ну, как бы, не знаю, для проблемы, наверное, знака, может, существенный, я не знаю, не сталкивался.
Для проблемы знака, в принципе, очень существенный, потому что Монте-Карло вы, скорее всего, вообще не сможете применить.
Ну да, и Монте-Карло это для системы, для модели Хайзенберга она работает, но для других более сложных фрустрированных моделей геометрии она еще хуже работает. Это еще один из случаев, когда Монте-Карло работает. И мы можем
для
проверить.
Для модели Китаева, например,
Вот.
я сомневаюсь, что получится Монте-Карло получить что-то вменяемое.
Ну, окей, может, make sense. Ну, просто кроме Монте-Карло есть же другие методы, наверное, расчета. Ну, в смысле, там, не знаю, ДМФТ вообще все катит или не катит, или не
Ну, это
катит.
среднеполевой метод. Там он очень неаккуратный, особенно в двумерии.
А почему надо за это
ДМФТ придется как-то сильно улучшать.
Почему надо бороться за модель Китаева? Чем она как бы хороша, где на хлеб мажется?
Для модели Китаева отлично то, что ее можно точно решить. И можно получить точное значение энергии, которое можно сравнивать потом с численными. И не только энергии, вообще множество различных наблюдаемых, которые можно найти точно и потом сравнивать с результатами численного расчета.
Что значит точно найти? Аналитически, что ли?
Да, она решается.
Угу.
В целом это методологические результаты, то есть если метод будет опробован на таких сложных моделях, то фактически можно и брать уже более широкие системы, в том числе, где не существует решений, но и есть экспериментальные реализации, да, и мы можем даже для экспериментаторов что-то предложить, предсказать таким образом.
Тогда понятно.
Ну, и если говорить про другие численные методы, то есть, конечно, несколько интересных, но, как мне кажется, пока что они не догоняют до того же Монте-Карло. И тензорных. Ну, вот есть, например, ну, тот же ДМФТ не модифицированно, это, конечно, не такое, но можно внести много модификаций в ДМФТ, там вот эти vertex методы, можно использовать
Ну,
диаграммные.
Диаграммные, да, техники всякие расширения.
То есть, если их добавить еще, то, возможно, ну, получится подойти как-то поближе к точности.
Ну, окей, хорошо. Спасибо.
Ну, я предполагаю, что это как бы удачный момент, чтобы еще поблагодарить один раз и завершить обсуждение темы семинара. Спасибо, Илья.
Спасибо.
Я останавливаю
Спасибо, Илья.
запись.
Спасибо.